So what do you have to do if you want to construct an ideal room? So in an ideal room, the sound goes down as an exponential. So very quickly does the sound go down. And more often than not, what we define the reverberation time as is the time required for the sound level to decrease by 60 decibel. Remember, I did not define reverberation time actually, but for room construction, we usually define reverberation time as the time that it takes for the sound in the room to go down by 60 decibel. It's very quick. You would like it to be quick depending on the room that you want. The way that's defined is KV over A, where K is a constant and it depends on the dimensions of the room. But for all general purposes for our class, I am always going to consider K as 0.161. So for us now, note this is not a standard, like this is not for everyone. Every single room will have its own K, but for our class, you can easily assume K will always be 0.161 seconds per meter. And V is the volume of the room, where that means is it's going to be its length times its width times its height. So if the length, width, and height of a room are given, find the volume. It will be given in meters cubed. And then the effective area of absorption. So for example, the walls could be absorbing, or there could be windows in the room. So find the area for the window, find the area for the wall, and that will be the effective area of absorption. Area will be length times width, given in meters squared. Okay, next, this is for an empty room. Now, what if the room is not empty, but it in fact has chairs, and it has a carpet, and it has these things, and all of these things absorb sound. So when you have these many things in a room, the way you would find the absorption constant is by multiplying them A1 by A1, which A1 are the different surfaces, and A are the areas of the different things. So for example, every chair that's in this room has its own absorption constant multiplied by the area of each chair. Same thing with the carpet, right? So this carpet has a particular area, and so we will use those. And there's also air. So if you are talking about absorption in air, we're going to use this formula. Again, standardizing K to be 0.161 times V, which is the volume of the room, A, which is the absorption constant, plus 4mV. M is the absorption constant, and I've given you some absorption constant in the book. So if ever this question comes, look it up in the book. So M, the value of M will be given. Okay, so now that we have those formulas, we can say that the reverberation time is a compromise between three things. One is how clear you would want your sound to be, how loud you would like that sound to be, and how lively would you want to be. For clarity, you want small reverberation time. You don't want my noise, you don't want my sound to be coming in with reverberation. It's going to be very disconcerting to hear a speech for more than like a couple minutes with a lot of reverberation. On the other hand, you want a high reverberation level for loudness, whereas for liveliness, you would like a long reverberation time. So every room kind of has to deal with all of those things. So it's a compromise between all of these. So for auditoriums, you want shorter reverberation times where speeches are being made, whereas if you have a music hall, you want a longer reverberation time. And it's all math, basically. It's so fascinating, right? All of the music you play is summarized in this one equation. Don't you find that fascinating?